I'm here today to talk about SDR tricks with HackRF, and HackRF is a software-defined radio platform that is my design and is currently being manufactured, which is why I'm not sleeping a lot lately. By the way, before I get started, happy Tau Day tomorrow. Does everybody know what Tau is? Tau, right? You might, those of you who aren't raising your hands may have heard of this number called pi, which is all wrong. Tau is the new hotness. Pi is old and busted. Tau is equal to twice pi. So if you're familiar with pi, 3.14, etc., tau is twice that, right? So it turns out that tau is actually a more fundamental number in mathematics, and people are starting to catch on to this. So a lot of people try to celebrate Pi Day on the date 3/14, like March 14th. So I celebrate Tau Day, which is tomorrow. And actually, this week I got, for the first time in my life, I got in the mail a Happy Tau Day card that came from Dominic Spill in the UK. So yeah, you can see we have a little work to do to get adoption of Tau Day going here, but I'm excited for tomorrow's Tau Day. And if you see me tomorrow, be sure to wish me a happy Tau Day. So this is completely in the wrong spot. I'll come back to that slide later. You'd think I would have made better use of that 2 hours I had this morning waiting around in my hotel room. So HackRF1 is a software-defined radio peripheral. It's primarily designed to connect to a host computer like a laptop and allow you to transmit or receive virtually any radio signal over a very wide operating frequency range. It can also be operated in standalone mode. It can also be used for a variety of different things. And what I want to talk about today is some not necessarily atypical applications of HackRF, but atypical ways to use the hardware. And I am talking specifically about HackRF because it's my design and I know a lot about it, but some of the things that I'll talk about today are tricks that could be applied to other SDR platforms as well. Just the details will be different. The main limitations of HackRF are kind of three things. One is it has a limited operating frequency range. Two is it has a limited bandwidth, which is a function of its sample rate. Its maximum sample rate is 20 million samples per second. And then the third main limitation is that it's half duplex. That means it can transmit or receive, but it can't transmit and receive at the same time. And all of these limitations actually have some wiggle room. And that's what I want to talk about today, is kind of how you can get around these limitations or what you can do outside of these limitations with the hardware. And to understand what I'm talking about, it's helpful to know a little bit about the architecture of HackRF. And this is an old slide, actually, from back when I was originally hoping that my operating frequency range would be 100 megahertz to 6 gigahertz. It's actually wider than that now. But the architecture still stands. So at the antenna, we can transmit or receive signals over this very wide operating frequency range. And then there's this section that I call the wideband front end. There's a mixer there, and that shifts the frequency. So it shifts the RF frequency to an IF. It shifts the radio frequency to an intermediate frequency. And that intermediate frequency is typically in the range 2.3 to 2.7 gigahertz. And then there's this next block, which is an IF transceiver. And it shifts the frequency, again, between the IF and baseband, which is the vicinity of 0 hertz. So those are kind of the three frequencies that you need to know about. There's baseband, which is around 0 hertz. There's the IF, the intermediate frequency, around 2.5 gigahertz. And then there's the RF frequency over a wide range up to 6 gigahertz. So there are two different frequency conversions that happen. And then there's an ADC-DAC, that's an analog to digital converter and digital to analog converter, which is actually all on one chip. And from there on, the digitized signal is passed back and forth over USB to a host computer. So the first thing I want to talk about is what you can do with that analog to digital converter or digital to analog converter other than radio. The device is designed for radio, but here's this pretty fast ADC and DAC hooked up to a host computer that you can stream samples in and out pretty quickly. It could be useful for a lot of different things. So I put this expansion header on HackRF. There are a whole bunch of expansion headers on HackRF. And the idea is, people should be able to hack it however they want. And so in this case, I have a couple of wires plugged into the baseband analog header. So it's in between the RF section and the analog to digital converter. So right now I'm just tapping right into the analog lines that go into that analog to digital converter. And this allows me to plug these wires or connect them to something else that I want to sample, any electrical signal that I want to sample. There are some limitations here. If you connect directly into the analog to digital converter, you get 2 channels of ADC, and you can get, but the signaling is differential. So similar to the way you have a pair of wires in an Ethernet cable, and the current goes one way on one wire and the other way on another wire, back and forth. And the receiving end is kind of measuring the difference between those 2 currents or voltages, depending on the type of ADC it is. And in the case of HackRF, it's measuring voltages or the voltage difference between those 2 wires, and it accepts as much as 1 volt peak-to-peak variation. And it expects that there's a common mode voltage that's somewhere in the middle of the operating voltage of the part. So you have to give it a signal that is within that range that it knows how to understand. And you also need to be aware that there's no anti-aliasing filter if you plug directly into the ADC. So it might be helpful to have some small circuit of your own that you plug into it. But even without doing much, just tapping in a couple of lines, I was just playing the other day with one of my favorite toys, the Hot Wheels radar gun. So a Hot Wheels radar gun is this great orange piece of plastic that shoots a 10 gigahertz radio wave at something and measures the return on it and tells you how fast it's going. It's just a regular old radar gun, very similar to like a police radar gun, but it's a continuous wave radar. And it has kind of 3 main components in it. It has a battery pack, it has this radar section, and then it has this separate board that you can see there with the little speed control and stuff, or the LCD on it. The little LCD control panel is a completely separate unit from the radar unit inside here. So I buy these things on eBay, and oftentimes they show up at my house broken. But usually the part that's broken is the controller. And if you just hack that off of the radar section, you can tap into those 3 wires at the bottom there. All you have to do is supply power to the radar section and then pick up the return off of it. Easy. And I plug in 2 of those wires to my HackRF. And here, let me show you a little demo. So I'm going to use GNU Radio Companion, which is a wonderful tool, visual tool for dealing with software-defined radio. And in this case, I'm taking a little waveform that I saved directly from my HackRF, and I'm going to play it and replay it over and over again and just visualize it. So I'm basically using my HackRF as an oscilloscope here. And so what I did was I just tapped into the Hot Wheels radar gun, plugged it into the direct ADC lines and baseband header on my HackRF, applied power to the Hot Wheels radar gun, and waved my hand around in front of it. And this is the resulting signal that I get. Pretty cool, pretty useful as just kind of a general purpose oscilloscope, as long as you understand the limitations of what you can plug into it and how that signal has to be conditioned, perhaps. But in this case, I was able to just plug directly in and visualize that signal. You can also do the same thing with the DAC, the digital to analog converter. So you can produce electrical waveforms in addition to analyzing electrical waveforms. And the goal here would be to produce a function like a function generator, and which is a type of electronic test equipment. And what I'm trying to do here is kind of use HackRF as a general purpose test tool. At its core, HackRF is an RF signal generator and an RF signal analyzer. But it could be used for more than that. It can be used as an oscilloscope, which I just showed, or it could be used as a function generator. But again, it has similar limitations or things you have to be aware of if you're going to plug into it. I'm working on a little baseband expansion board that will make these things easier to use. So you could use HackRF as an oscilloscope just by taking off-the-shelf oscilloscope probes and plugging them into a BNC connector, and then, using it as a regular oscilloscope instead of having to deal. It would just take care of some of those limitations for you. Or you could interface HackRF with an external front end. And one thing that's interesting to note about this approach of tapping directly into that baseband header is that the HackRF design is half duplex, but it's only the RF section that's half duplex. From the USB connection through the analog to digital converter and digital to analog converter, it's actually full duplex capable. We don't have any firmware that takes advantage of that yet, but the hardware design is actually full duplex. So it's possible if you plug in your own RF front end to the baseband connection, or if you just want to do simultaneous function generation and oscilloscope probing, you can do that in theory. Now I want to talk about the operating frequency range. The design goal of the HackRF project was to build an open source hardware platform that could kind of support the widest possible array of applications that we can think of. And an important part of that is having it operate over the widest range of frequencies we could support. And originally we thought, well, let's try to support 100 megahertz to 6 gigahertz. And then after we selected components, I kind of looked at the parts that we had and said, well, hey, this thing ought to work down to 30 megahertz. And then I started prototyping and building things, and I made the beta platform, and quite a few people have those HackRF jawbreakers, the beta units. And at that point, we kind of found out that it worked okay down to around 10 megahertz. And that got me thinking, well, maybe we could even do better than that. So I started to tweak, kind of swap out components for other components and try to improve the low frequency range without adversely affecting the high frequency range, which is a little tricky. But now I'm going to go back to that slide that I had at the beginning that I shouldn't have been there. After I show you a little review of the architecture, the operating frequency is a function of these two mixer sections, the wideband front end and the IF transceiver. And each one of those has its own frequency, and the RF, the radio frequency, is the sum or the difference of those two frequencies. So if the IF is at 2.5 gigahertz and the front end mixer is at, say, 2 gigahertz, then the RF is at 2.5 plus 2 gigahertz or 2.5 minus 2 gigahertz. So it's either at 4.5 gigahertz or it's at 500 megahertz. So depending on the range of those two components, the operating frequency range, we can choose whatever RF we want. And because the wideband front end mixer actually has a wider operating frequency range than the intermediate transceiver does, that means we can tune all the way down to 0 hertz without any trouble. The trouble is what kind of performance do we get around 0 hertz. So there's no limitation against you tuning to 0 hertz. It's just what will you get there. So I'm going to show you a plot that was way at the beginning of my talk, right there. Okay. So this is a plot I took a couple months ago from one of the prototype HackRF units that has already shipped. And this is the maximum output power, the transmit power, from 0 to 10 megahertz. Now 10 megahertz at the far right side of the graph, that's the lower end of the official operating range. But as you can see, the performance is really quite good far below 10 megahertz. And I haven't really advertised this. I haven't changed the official specification because I don't know how much I can guarantee here. But this is a result from one particular unit. And it looks to me like it performs pretty well down to about 1 megahertz. And there's some performance. There's a significant drop-off in performance below 1 megahertz, but you could actually do some things below 1 megahertz. So as an example, as kind of an extreme example, I wanted to play around with RFID. A lot of people, when I lowered the operating frequency range from 30 megahertz down to 10 megahertz, a lot of people said, "Ooh, boy, now that's exciting. We can do high-frequency RFID stuff." But 2 orders of magnitude lower in frequency, down around 125 kilohertz, which is around about the little spot where there's the dip at the bottom of this plot. That's where low-frequency RFID operates. And I'm going to skip back to my place in the slides where I should be. So here's what I did. I plugged in a coil of wire into the antenna connector on HackRF. Now this is potentially dangerous. If I were to transmit here and turn on my transmit amplifier, I might actually damage the little amplifier in HackRF. But if I'm just receiving, I can use this crude loop antenna. And what I did was I just held this up to a RFID reader and held an RFID tag next to it. And I took a little recording of that also. Let me show this to you in GNU Radio Companion. So I'm going to loop through this recording, and I'm actually going at 1/4 of actual speed. Now look to the left and right of that big center spike, and you'll notice something there. You see that? You see that? You see all that stuff to the left and right of the center peak? Now we just get the center peak again. So what's going on is the RFID reader is sending these pulses at 125 kilohertz. And I've centered this graph at 125 kilohertz. So where it says 0, that really means 125. And then when I hold, and so I'm getting these pulses from the RFID reader, and then a tag is present, and all those little spikes on either side of 125 kilohertz, that's actually the modulated data being transmitted by the tag. So I was actually able to successfully decode RFID signals, low-frequency RFID signals at 125 kilohertz, which is just an absurdly low frequency, using this really crude setup, just plugging in a piece of wire into, or sorry, a loop of wire into the front end of the HackRF. Now, the last thing I want to talk about, I'm not sure exactly how much time I have left, but it's about noon, right? And if people want to have lunch. The last thing I want to talk about is the high end of the operating frequency range. Now, there was, now I mentioned that the RF, the radio frequency that the HackRF is tuned to, is the sum or difference of those 2 mixer frequencies. The one mixer can go up to about 2.7 gigahertz. In reality, it can go up to about 2.75 or 2.76. And then the wideband front-end mixer, I think it's advertised to go up to something like 4.2 gigahertz, but if you read the data sheet and look at how it can be configured, it can actually go up to 5.4. So we can tune to the sum of 5.4 gigahertz and 2.75 gigahertz, which is about 8.15 gigahertz, much higher than the advertised operating range of HackRF. So let's just try that and see what we get. So this next slide, this is a plot. I only have one piece of RF test equipment that goes above 6 gigahertz, and it's this old spectrum analyzer that goes to 7 gigahertz. So I configured my spectrum analyzer here to show me the range from 4 gigahertz to 7 gigahertz. That's as high as I can go with any calibrated test equipment in my lab. This yellow line, the yellow plot on this is the result of me tuning the HackRF and stepping it through a whole bunch of frequencies from 4 gigahertz all the way up to 7 gigahertz, and just seeing what the absolute maximum output power I can get is out of the thing. So as you can see, there's a pretty significant performance drop-off from 4 gigahertz down to about 5 gigahertz, and then it recovers a little bit. And then the little marker, that little 1, is actually at 6 gigahertz. So between 5 and 6 gigahertz, the performance improves a little bit and then declines a little bit. And then above 6 gigahertz, it drops off dramatically. However, there is still usable output signal well above 6 gigahertz, and it goes up. This plot goes up to 7. Presumably, it would keep dropping off at that precipitous rate above 7 gigahertz, and I doubt that it would be very usable. However, let's talk about this little blue line. The blue trace is the result of a different operation. Here, what I did was all I did was I tuned the HackRF between 2.15 and 2.75 gigahertz. That's the range that the intermediate frequency transceiver operates in. I completely bypassed the front-end mixer and just run that intermediate frequency right out to the antenna. Now, I should be seeing a significant output between 2.5 or around 2.5 gigahertz, but that's off the left-hand side of this plot. We're not seeing that. That output would be up above 10 dBm. But what we are seeing is 2 sections of this blue trace. It goes from about 4 gigahertz to 5.5 gigahertz, which is twice the intermediate frequency. And then it goes from, over on the right-hand side, we have 3 times the intermediate frequency. So what we're seeing with these blue plots is actually the harmonics of the intermediate frequency. And in some cases, especially on the very high end, we can actually get better maximum output power from the transmitter, like way up at 7 gigahertz, just by exploiting the harmonics of the intermediate frequency instead of actually trying to mix it up in that front-end mixer. Now, the fact that these blue curves aren't very flat, and especially the fact that we get that really extreme peak around 4.9 gigahertz, that's a result of the fact that I'm actually overdriving the front-end amplifier. I'm driving it into distortion, very similar to the way electric guitar can be driven, a guitar amp can be driven into distortion, which enhances the harmonics. Same exact thing happening, except we're in gigahertz instead of hertz. And so it's the fact that I'm pushing the limits of the amplifier that we get kind of this crazy curves and peaks. But it shows you that by using a dirty trick like exploiting the harmonics of the IF, we could actually do things potentially useful up around 7 gigahertz that we wouldn't be able to do by configuring it in the traditional way. And in practice, you probably wouldn't ever want to do this unless you also put your own filter in the front end to filter out everything other than the harmonic you want. But that's very easily done. And that's all I have for you today. Are there any questions?
So, very interested in you being able to do the RFID level stuff. I know you can buy external stepper uppers, that will take a low frequency and put it into the more comfortable range. But what would you need to do to make it more safe to step up the 125 kilohertz rather than just a little coil? Like, what would be the proper way to?
Sure. Okay. So he's very interested in low frequency and RFID stuff in general, right? And other than my crude hack of plugging in a piece of wire, what's the right way to do this? Is that the question? Yeah.
Well, like I said, I know there's third-party devices you can buy for like $40 that'll step it up. But is there a way to go about it that would be safe to put this on the front end? You said there's a risk if you were to try to transmit, for example, out of this. Or.
Right. So there are a couple of different things to consider here. One is, as you mentioned, there are up converters available. Like the ham it up converter is one that I'm really fond of because it's open source hardware, just like HackRF. It's designed by a guy in Canada, and it's readily available. It works well for both transmit and receive, and it lets you operate like where I showed that really long curve going down from 10 megahertz down, and then it precipitously drops. Right? If you use ham it up, you get a pretty flat curve all the way from about 10 megahertz to 100 kilohertz. That's about where the 3D point is. So a much more flat performance. However, if you're dealing with RFID in particular, RFID is a little bit of a weird beast because it's not really doing radio transmission. It's using direct coupling, inductive coupling. So it's just like an electrical transformer. If you take half the transformer in the reader and half the transformer in the tag and put them next to each other, and then now you have a full transformer. And so it's using this direct inductive coupling instead of what we think of as traditional radio propagation, and that's why you can't get very much range out of low-frequency RFID systems. And because of that, just plugging in an antenna and expecting it to work with RFID doesn't really work. And I'm just talking about low-frequency and high-frequency RFID, where high frequency is really down around 13 megahertz. There are different types of RFID systems at much higher frequencies that do propagate over greater distances. But in particular, like this solution of plugging in a little piece of wire doesn't let me transmit, doesn't let me spoof a tag. It lets me sniff what a tag is transmitting, but it doesn't let me actually spoof a tag because I don't have any direct way to kind of modulate the signal that the reader is giving me. So I have to have some kind of an active circuit on that. And I'm actually probably in the next issue of POC or GTFO going to have a little article that talks about how to do that with equipment that's even simpler and lower cost than HackRF. So that's kind of the magic piece that you need for dealing with RFID systems if you want to transmit and receive, is some little active circuit there that helps you take the signal that you're transmitting and use that to modulate the signal that the RFID reader is transmitting. Another thing to keep in mind is that arguably, instead of plugging into the front end like I did there for that RFID demo, I could have plugged into the analog baseband. And actually, at that level, I have much flatter performance down to the vicinity of 0 hertz. So that's arguably a better way to use HackRF at those frequencies. I just wanted to see how far down in frequency I could go on the RF, and that's why I did it that way this time.
It would be really cool to see in your article something about using the header extensions to be able to do that as a dual-purpose device. That'd be awesome.
Oh, yeah. Actually, the article is going to be not about HackRF, but using sound card hardware for the same kind of thing, but it would be applicable. Yeah, cool. Any other questions? Are we done? Is it lunchtime? All right, I think it's lunchtime. Thank you, everybody.